Good afternoon. We are going to do the fourth session in automotive engineering. So the topic today is combustion. So we are going to learn the conditions necessary for combustion, how to balance chemical equations, and then we'll talk about what is called stoichiometry. So you should have learned this in your A-levels, but we are doing it to a slightly deeper depth here. And understanding of formation and health risks of pollutants is another topic that we are going to learn today, and so that's what we will be doing. So combustion, the chemical equations, calculation of stoichiometry, and what happens if you don't find it stoichiometry, and emissions. Okay. So there is a concept called the fire tetrahedron. It's a fairly simple concept. So for combustion to take place, you need oxygen and oxidant rather, and fuel. And the fuel and oxygen mix together and do a chemical reaction, and it will produce heat. You need to have some activation energy as well. So if you don't reach to a certain temperature, the combustion won't take place. But once it has started, it goes as a chain reaction. So the results of these are the emissions or the results or the products of combustion and heat. So we do combustion for mainly for heat. Sometimes you do it for light as well, but we are not going to consider that in here. And if you look at different energy sources, we'll look at the energy density and the specific energy. So if you look at energy density of diesel and gasoline, they are pretty high. Megajoules per liter is pretty high, and LP gas is somewhere around there. But all the other sources like ethanol or dimethyl ether, now these ethanol can be produced using bio. It's a biofuel basically, and methanol is also can be produced using biological means, and the problem with the present day batteries is the energy density is quite low, still quite low, and specific energy or megajoules per kilogram is also quite low for batteries, and both these are quite high for diesel and gasoline and LP gas also. And megajoules per kilogram per hydrogen is the highest, but if you take it in a volumetric sense, that means hydrogen as a gas, it doesn't have a good energy density. But if you can pressurize it, you can have a really high energy density with hydrogen. So hydrogen's energy density, specific energy density is like nearly 3 times, rather more than 3 times LP gas, gasoline, or diesel in any other form. Then you look at the hydrocarbons. Hydrocarbons, if you remember, hydrocarbons are the most basic hydrocarbon is methane. Then the number of carbon molecules and hydrogen molecules increase. Ethane has C2H, has a chemical formula C2H6. Propane is C3H8, and then C4H10 is butane. Octane is C8. H18. So octane is the is the first one that has an aromatic shape for the molecule. So the others are linear chains. So there are T's of combustion. We call them 3 T's of combustion. For the combustion to take place, you need sufficient time for chemical reaction, and then you need sufficient temperature. So that means if you don't reach enough temperature, well, reach the activation temperature, time combustion will not take place. For example, if you have a bottle of if you have a beaker of petrol, and if you leave it in if you just leave it in the atmosphere, it doesn't burn. So you need to ignite it. So you need to bring it to the self ignition temperature for the combustion to start. And then you need to have sufficient turbulence to mix. So you must have seen that some fires just extinguish just because it can't continue continue the chain reaction because you don't have enough turbulence in there. So combustion chemistry. So we'll go to an A-level combustion, advanced level combustion problem basically. We will look at the methane example. So methane is CH4. Yeah, that's your CH4 is the chemical formula for methane. So if you look at combustion, carbon burning with oxygen will produce CO2. C plus O2 is CO2, and hydrogen. If you write the chemical equation for hydrogen burning, H2 is plus half O2 will produce H2O. So these two are balanced chemical equations, and then if you have 2H2, it will mix with one oxygen molecule, and it will produce two H2O molecules. So then you can write the balanced chemical equation for CH4. So we'll say CH4 will mix with will react with a number of O2 molecules, and it will produce B number of CO2 molecules plus D number of H2O molecules. So how do we balance this? So how to balance this is okay. On the left hand side you have one C molecule. That means on the right hand side you should have one C molecule as well. So that means one here should be one here. So B should be equal to 1, and then so that's your first step. Okay. So balancing C atoms, your B should be 1. Then you can look at so your B is 1. That means this O2 is 1, and then if you look at H4, okay, so on this side you have H4. So H4 means 2H2. Yeah. So 2H2 will burn with oxygen O2 plus it will produce 2H2. So 2H2O. So that means if you had a number of H2 here, that means 2 H2 will produce 2 H2O. So that means balancing for H atoms, 4 equals 2D, D should be 2. And then balancing oxygen atoms, so A O2 is equal to 1 times O2 plus 2 times O here. So that means 4. So A should be equal to 2. So your balance equation should be CH4 plus 2O2 will produce CO2 plus 2H2O. Okay, so that's the balanced chemical equation for methane. So then, that is we have been looking at moles here, or number of atoms, number of molecules here. So then we now we have two methods of looking at this. One is the gravimetric analysis, and the other one is the volumetric analysis. So then we will go back to some of our A-level chemistry again. So if you want to analyze the combustion equation by mass, how you do this is you need to look at the molar masses or molecular masses of carbon, hydrogen, and oxygen. So the molecular mass of carbon is 12. Molecular mass, atomic mass of carbon is 12. Atomic mass of hydrogen is 1. Atomic mass of oxygen is 16. Okay. So if you look at, so that means in CH4 you will have. So if you take one hydrogen, if you take 1 hydrogen kilogram, so we can say the rest for you need the equivalent of carbon is 12 kilograms. Okay, so the same number of molecules in carbon will have 12 kilograms of weight. Okay, so therefore with that analogy, we can say this is CH4 will weigh 16 then. So hydrogen is 4, carbon is 12. So 4 plus 12 is 16. 2O2 means 2 times 32, which is 64. CO2 means 1 times 12 plus 16 times 2, which is 44. H2O is 1 H2O is 16, whereas how you get that is sorry. 1 H2O is 18. 2 H2O is 36. So how you get that is H2 is 2. O is 16, 2 plus 16, 18, 18 times 2 is 36. So 1 kg of CH4 will react with, so if you divide this by to balance for 1 kg of CH4, so you divide everything by 16, so 1 kg of CH4 will react with 4 kgs of O2, which will produce 2.75 kgs of CO2 plus 2.25 kgs of H2O. So this is the basically the gravimetric analysis of the mass ratios of combustion for CH4. Okay, so by mass then so you need 4 kilograms of O2 to combust with 1 kilogram of CH4. Okay, so the gravimetric ratio is 4 to 1. Okay. So the relative molecular mass of M substance kg is called a kilomole. Hence, 16 kilograms of CH4 is 1 kilomole of CH4. So a kilomole is 16 kilograms of CH4 is 1 kilomole of CH4. So the molar mass of CH4 is 16 kilograms. Okay. So then we will look at volumetric analysis, or the how we can look at the volumes of CH4. So CH4 is a gas, O2 is a gas, CO2 is also a gas, and H2O in combustion is a gas. Okay, but you can condense that and get rid of it if you want. So 1 kilomole of CH4 will react with 2 kilomoles of O2 plus 1 kilomole of CO2 plus 2 kilomoles of H2O. But according to Avogadro's law, 1 kilomole of any gas will have a certain volume. That volume is fixed. So 1 kilomole of CH4 will be equal to 1 kilomole of the volume of 1 kilomole of CH4 is equal to the volume of 1 kilomole of CO2, or the volume of 1 kilomole of O2. Okay, so 1 kilomole of any gas is at standard temperature and pressure will have the same volume. Okay, so using that, if you look at this equation, you can say CH4, 1 kilomole of CH4 plus one volume of CH4 will react with 2 volumes of O2, and it will produce 1 volume of CO2 here plus 2 volumes of H2. Okay. Then we know that so you need to know those two first, and then we know that we don't burn CH4 in pure oxygen. What we do is we burn CH4 in air. So air has 21% oxygen and 79% nitrogen, and that means 1 unit of air will have 0.21 units of O2 and 0.79 units of N2. So that is by mass. This is by mass. This is, if you want to get it by volume, you will have one over 2.21 moles of air plus 1 will produce will have 1 mole of O2 plus 0.79 or 0.21 moles of N2. Okay. So therefore, for each mole of oxygen, we have approximately 3.79 moles of nitrogen. Okay. So therefore, if you get the molar mass, if you include nitrogen into this equation, what we do is you will have CH4 here, 2 times O2 here, and then you have to add 79 by 21 N2 times 2 to balance the N2. But that N2 will not react. Therefore, you will have the same on the other side of the equation, and these two don't change. CO2 and H2O don't change. Okay, so that's what all that we do. So these volumetric ratios were defined by Avogadro. Basically, Avogadro said the volume of gas at a given temperature and pressure is proportional to the number of atoms or molecules regardless of the gas. Okay, so that means 1 kilomole of hydrogen is volume of 1 kilomole of hydrogen is equal to volume of 1 kilomole of H2 or H2O, or 1 kilomole of CH4, or 1 kilomole of CO2, or 1 kilomole of CO. They'll say. And then there is, he defined the number of atoms or molecules in 1 mole. So that would be 6 times 10 to the power 23 atoms. Okay, so that's called the Avogadro's number. So in the above equation, so you have 1 kilomole or 1 mole of CH4 plus 2 moles of O2 will produce 1 mole of CO2 plus 2 moles of H2O. But when we do combustion experiments, what we do is we condense the water. We take the water out and compared to the volume of air, the volume of water is really negligible. Therefore, you can discard the volume of that. Okay. So then your equation becomes 1 kilomole of 1 mole of CH4 plus 2 moles of O2 will produce 1 mole of CO2 and 0 moles of H2O, 0 volumes of H2O. Okay. So these are by volume. So then once we have written the equation CH4 plus O2 plus 2O2 plus 79 by 21 times 2O2, then you will have then you will have the equation here. Okay, so then we can calculate the air fuel ratio. So we will go to that in a second.